Hello, welcome to the lecture 37 in the video 37 in the lecture Advanced Mathematic Modeling. So we are discussing in the moment power law distributions. They appeared in the lecture because we were interested in random walks which have super diffusive behavior, and that's one way to obtain super diffusive behavior if the increments are taken from a power law distribution. But then I decided to discuss power law distributions in general, independent from random walks, because they have so interesting properties and are so important. And so power law distribution is a distribution where the random number goes to a power with an exponent alpha, minus alpha, and alpha we saw is in the range between 1 and 3. And so this distribution looks like this. Here, so we have this decaying distribution, meaning we have a cutoff value, the smallest possible value, and then we have many small events, and few but very large events. So we get this very imbalanced distribution, which on a log scale is characterized by a straight line. And so we've seen all kinds of formula, how to calculate the moments, the cumulative distribution, and normalization. And so there is a lot we can say about this distribution, but I want the discussion of to start the discussion of this distribution with the observation that we have this imbalance. How can we formalize this a little bit more? And this leads us to the inequality of a distribution and the Pareto rule. So what do we mean by this? So, but first, maybe going back to the power law distributions, we saw that depending on the range of alpha, when alpha is smaller than 2, the distribution doesn't have a mean anymore. So the average value diverges. So this means like for alpha smaller than 2, the distribution is so broad that we cannot really, at least from expectation value, tell us what's the typical value that we will obtain. But we can still obtain a typical value if we look for the median. And I want to show you this now. So, but let's start. So if alpha is smaller than 2, here, the mean doesn't exist. And of course we are speaking here about always power law distribution, because this holds only, of course, if we have this power law distribution. But we can define the median. And we know how to define the median. So the median is defined as the value x 1 over 2, so that we integrate our distribution p of x dx from the median to infinity. This should give 1 over 2. And so since the whole distribution is normalized, so this is just 1/2 of I mean that just the whole integral over the distribution p of x dx, and due to normalization that's 1 over 2. Yeah. And now we just have to work out this integral, but I don't want to repeat these calculations. We have seen these integrals very often, and so you plug in this power law here, integrate this, set this to 1 over 2, and then we find that the median of power law distribution is defined as 2 to 1 over alpha minus 1 times x0. That's one other formula that we can remember. So generally we usually it's enough to look for the mean value. So let's see, for comparison, here this was the mean value of a distribution, and that's typically enough. And usually we can calculate stuff more easy with this value. But for power law distributions or other cases with which not enough data or something, it's very often more in the median gives a more sensible result than the mean. And maybe here for a visualization, if we would have a distribution which is not a power law, which is more like a Gaussian, let's say we have such a distribution, and we have here p of x, and then the median is the value of the distribution. Yeah. So I just want to show like that the left area here equals the right area, but it's not necessarily the mean. Maybe here in this case it would have been a bit more to the side. But what's important, it's not necessarily in the maximum of the distribution and not necessarily the mean. So it's defined in such a way that in the left half the area equals the area under the distribution in the right half. Or if we plot here the cumulative distribution, but we take the p larger, so the fraction of random numbers larger than value x, and so this is a decaying function. And then for the median we look where is this function where has it decayed to 1 over 2. And now I was not careful with my sketch here, because this and this of course should be the same value. Yeah, so I didn't, because I roughly sketched this. So like, of course, like if you have the cumulative distribution, you look where is it decayed, for which value has it decayed to 1 over 2. This is the same value, the median, where both areas have the same value. Now for but if we have a power law distribution, so like this is typically, I mean, the picture, it's more easy to, when you have such a distribution, to visualize the median. But if we have a power law distribution, okay, so then our distribution looks like this. So we have a cutoff value x0, p of x, and so the distribution decays and can have very, very large values. Then the median is maybe somewhere here. And again, we mean that, so that's the smallest value, that the area on this side equals the area on the curve of the right hand side. And if we look at the, again here, p larger of x, cumulative distribution, which now decays from 1. So at the cutoff value it has the value 1, and then it decays also as a power law, as we have seen. And in this value here it has decayed to 50%. Yeah? So and so that's the meaning of the median for such a power law distribution. And for the purpose, for the sake of the following discussion, I will always take the example a wealth distribution Yeah. So the distribution of wealth in the population, and then this curve tells me what is the fraction of people, yeah, that have a certain wealth. And then you see in this curve that you have a lot of poor people and a few super rich people. And of course, and then this, the real distribution is approximately, can be described by a power law. And the slope of the power law tells you then how rich are the rich, or how many of these rich guys do we have in the distribution. And now, what does now the median value tell us? Yeah. Yeah. When we consider this value for this distribution, then of course the median gets some nice interpretation, which makes it again a bit more valuable than the mean, because like this is a typical split. Like we can now split the whole distribution of people into the poor people and the rich people. Yeah. So we can say x1/2, the median. This we can define, that's a typical wealth that separates the rich half of people from the poor half. Because like the problem is when we have a power law distribution, yeah, so and then we would like to know, for example, what is the typical value that a person has here. So if alpha is smaller than 2, the expectation doesn't even exist. So then we would say from the expectation, the typical value people have is infinite. Yeah, so meaning that, so it's very, very rich. But if we have this median, yeah, so x, we have 1/2, then we would say, okay, that's a typical value that exists. Yeah? And this splits because like half of the people there have a wealth smaller than this, and half of the people have a wealth larger of this. So that's a typical wealth which splits the population exactly in the middle. Yeah. And now let's calculate this. So for example, if we have we can make a small table. So let's say here we have a typical exponent, and here we have the median, and here we have the mean of the population. And now we can just calculate this. Let's start like with exponent 3. So I have already filled out this table. So if we have an exponent of 3, so that's a large exponent, so then the mean value of the power law would be 2, and the median would be 1.441. So here I assume the cutoff is at 1. So the median would be 1.4 times the median wealth would be 1.4 times the wealth of the poorest. Yeah? And here median and mean are not so different. Now if alpha is reduced and we have 2.1, then the median is 1.87 and the mean is already 11. And if alpha is 2, so that's the border where the mean is defined, so the median still exists, and this is 2 times the x0, whereas the mean already diverges. So this means, and now from now the question, what is the alpha when you fit this for wealth distribution? And this depends a little bit what data set you look, what country, what kind of data, and but so typical value is something like alpha equals 2.1. So that's a typical value for for wealth distribution, but also for many of the other power laws that I discussed before. So this would mean if we now split the poor and the rich half of the population, we would have a value 1.87. Yeah? This means half of the population doesn't even have 2 times the money of the poorest, yeah? And the other half, the rich half, has then incredible high values of wealth. Yeah? So really the whole wealth is concentrated in the rich, and half of the people have basically the same as the poorest guy. Okay, now we can even look more careful. We can look what is actually the wealth here, because like this area here is only the number of people which are poor, and this is the number of people which are rich, and this is just here half-half. What is the wealth that is accumulated in the rich half? That's another question. What is the wealth that is accumulated in the rich half of the people? So how much money do they have? And in order to calculate this, we need now to see how much money is in there. So we have to weight the number of people with a certain wealth with the wealth. And then we integrate this from our median to infinity. And this we divide to the total wealth which is in the population. And this is now not normalized, because the total wealth is the number of people weighted with the wealth of the people. And so here we integrate then over the whole distribution, integrate over dx. Yeah. And then when you see, so that's just x 1 over 2 divided by our cutoff, and then this goes to power minus alpha plus 2. Yeah, so that's always the typical calculations there. You can easily calculate this integral. So, and now we can plug in our formula for the median. We can plug in this here, and then we see this is 2 to the power minus alpha minus 2 divided by alpha minus 1. Yeah? But this integral is only defined if alpha is larger than 2. Yeah? Because like if alpha is smaller than 2, then this integral already diverges. Yeah? And this means the typical wealth in the larger part of the people is infinite. Yeah? So this, when we want to calculate how much money is really accumulated in the rich people, we need a power law which is a bit mild. Yeah? Okay, now when we now have alpha equals 2.1, yeah? So then we calculate this, then we find this here leads to 2 to minus 0.09, and this is about 94%. So this means 94% of wealth is in the rich part of the people. In the rich half of the people. And this tells us something about what such a power law means here. So like the typical wealth that divides the rich and poor is only 0.09 0.9 or something. Yeah, so it's very close to the poorest value. And if you look how much wealth is then contributed in the rich people, so the rich half of the people has 94%. Yeah? So really most money is in the rich people. And so this tells you something about the inequality of the distribution. Now, but once, when we have gone so far, we can of course continue and extend this analysis and say, why did we choose here just the median? Yeah? So why did we divide the population exactly here in the middle? Of course, now we can change this value here and can ask how much wealth is in some other fraction of the people. And this leads us to the Gini curve and the Lorenz curve. So let's see what we mean by this. So we make a generalization. And so now we define first the quantity. So first again, what was this p larger of x? So this was the fraction of people which have wealth which is larger than x. And now we can define another quantity, w of x. That's the fraction of wealth that is occupied, that these people have, fraction of wealth that these people have. And let's see, how can we calculate this W? So it's very similar to what we had before. Only in the before we were calculating this exactly from the median, but now we take an arbitrary fraction x, and then we have the same formula. So we have here a fraction. So we calculate from an arbitrary value wealth to infinity. We integrate x p of x dx over the integral over the whole range from x0, x bar, p, x bar, d, x bar. And then you can do the same calculation as before, and we see this is x over x0 to power minus alpha plus 2. And now we can remember our formula for the cumulative distribution. So the cumulative distribution, this was this here. We had this before. Maybe I write this again. I've written this as a reminder, very small, maybe hopefully you can still read this. That was this formula. And now we can plug in this formula here. And then when you do this, you see that we can express the wealth in a certain fraction of people. Yeah? So in the fraction of people who have a wealth larger than x as a function of the fraction of people who have a wealth larger than x. Yeah? And this goes then to power alpha minus 2 divided by alpha minus 1. So you see, when we have calculated for a certain x value the cumulative number of people, so the fraction of people who have wealth larger this, we directly have then also the wealth obtained in these people. And this expression we can put in a in a curve. We can graphically represent this. So we make a graph. And here we plot the cumulative fraction. And this goes between 0 and 1. And here we plot the wealth, the fraction of wealth, which also goes between 0 and 1. So here you see this graph. So here we have the fraction of wealth in the population. Fraction goes between 0 and 1. And here we have this p larger of x, the fraction of people which have a wealth larger than x. And so, and these quantities are related. And I mean, if we have a fraction of people 0, they have fraction of wealth 0. And if we have 100% of people, they have 100% of wealth. But in between we have a curve. And this curve looks like something like this. Now it depends, of course, on the alpha. And this is how such a curve looks for alpha equals 2.1. Yeah. So this means we have, if we have increasing fraction of people, yeah, then we see increasing wealth in the people. And for example, if we take here the point 1/2, 50%, yeah, and then we would find here that would be a value 94%, 0.94, because we have seen, if we divide the people half-half, yeah, then 94% of the money is in the rich part of the people. Yeah. But now, so like this was what we calculated in the slide before, but now we can change the fraction of people and see how much wealth is there. And then, so one typical thing is, if you take here this point, if you take here 0.2 and have here 0.8, yeah, then the curve typically goes through this point here. But this, of course, it's only a rule of thumb. That's not a real strict quantitative law. But this means, so typically that 20% of the people there have a wealth of 80%, have 80% of the wealth in the population. Yeah? And this is sometimes called then the Pareto rule. Maybe I write this here. The Pareto rule goes like this. That we say, so sometimes it's called the 80-20 rule. And it says that 80% of wealth is accumulated in 20% of the richest people. Or so historically, Pareto found this for ground, how much ground, so land you own, and he found 20% of population owns 80% of the land. Yeah. So sometimes people use this 80-20 rule to say with 20% of effort you reach 80% of effect. So with the first effort you do things, you reach a lot, but if you want to reach 100% you have to put a lot of effort into things. But this is, I mean, so this Pareto rule, as we found this here, I mean, it really depends on the fact that we have a power law distribution, and then it depends on the exponent. And for an exponent about 2.1, I mean, we have approximately this 80-20 rule. But this is there's so many examples that people generalize this to others, to generic systems, and then they say, okay, with 20% of effort you gain so and so much percent of the effect. Or, I mean, if you can take other distributions, for take city sizes, and then typically we say 80% of people live in 20% biggest cities, or power law distributions also rule social contacts, and then you can say 80% of phone calls you get from 20% of most important contacts. Or you get 20%, 80% of emails from 20% of people, yeah. Or 20% of websites have 80% of traffic. And I mean, and the list can go on, but remember, these are not precise statements. It's a rule of thumb, and in general this can be a bit different. But I mean, and it always depends, do you really have a power law in these distributions? But for city sizes, social contacts, and so on, wealth and people, that's typically the case to very good approximation. And then, I mean, now in a real system it could be, instead of 80-20, it could be 70-30 or something. Yeah, so like that's just a rule of thumb, and we just explored here 2 points of this curve here. We explored the point when we have a fraction of 20% of richest people or 50% of richest people. And with this expression we can continue this curve all over. Yeah? And this curve is called the Lorenz curve. But since this video is getting too long, I will make a break now and we continue directly in the next video. Thank you.